All right, howdy. Today we are going to wrap up our discussion on similarity, and that will complete what we have to say about chapter 4, and then we're going to move on to chapter 5, which begins with orthogonality. So last class, I introduced the notion of similarity. So let me remind you guys of the context. So here was our setting. We have a linear transformation between two vector spaces. Say L from U to V. And we have two different bases. So we have a basis, actually, let's do things the simplest way. And we're going to make our domain and codomain be the same. And so we have two different bases. We have a basis, E, consisting of vectors U1 through UN. And we have a basis F, consisting of vectors V1 through Vn. And then associated to each of these bases, we can look at the corresponding coordinate vectors of U. So, just to remind you guys, everything in the vector space U, so like if you give me an arbitrary little vector V in U, we can write it as V equals A1 U1 plus A2 U2 plus blah 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 AN UN. And these A's form the component vector of the vector V. And so we can basically take all of these A's and we can group them together, and we get a vector A1, A2, AN, and this lives in Rn, and this is the coordinate vector. Of V. And we give a subscript to this Rn. The base is E to indicate where this coordinate vector came from. So when we use coordinate vectors, we can take our linear transformation L and we can understand it as a matrix on coordinate vectors. So L here corresponds to a matrix that takes Rn to Rn and takes coordinate vectors in E to coordinate vectors in E, and it's given by a matrix A. Now likewise, we could have done a similar thing with our basis F, and we could have looked at coordinate vectors with respect to the basis F, and so we'll denote that space of coordinate vectors like this. And in this case, L determines a map from this Rn to this Rn, modeled by a matrix B. Now, what we wanted to talk about last time was the relationship between the matrix A and the matrix B. And in order to express that relationship, we have to understand the change of basis. So the change of basis corresponds to how you go from a coordinate vector in the E basis to a coordinate vector in the F basis. And so you have these change of basis maps, call them V, and this whole square commutes, which is a way of saying if you start here and you go over on the right and then you go down, it's the same thing as first going down and then going over on the right. So this tells us that A times V is the same thing as B times V, which upon multiplying by the inverse of V tells us that VA V inverse is equal to B. And so B is similar to A. And so often the problem we face when we are studying similarity problems is we're given the matrix A, and it's with respect to some basis that we understand very well, and then we're given a second basis F, and we're asked to figure out what our linear transformation looks like with respect to the second basis. And the basic principle of computing it relies on this relation. You find your V, and then you basically multiply V on the left, V inverse on the right, on A, and that gives you B. So that is the process of computing B. So I want to do one more example today of how this goes, because you will be doing a lot of these computations in the near future. So I'm going to go through this one very carefully. We have a linear operator L from R3 to R3, and it is defined by this matrix A. So because we're going from R3 to R3, we're implicitly using the standard basis. So to write down my diagram, I have R3 here, and I'm going to write STD here to indicate that we're using the standard basis. And here it's modeled by the matrix A. And what we want to do is we want to consider what this linear transformation looks like to a second basis. This V1, this V2, and this V3. This way, with respect to the V basis, we can find the matrix B representing the linear transformation. So here's what we have to do. We have to understand how we can change basis between V basis and standard basis. So there's an easy way to do this, in one direction at least, which is that we can easily change from the V basis to the standard basis via a matrix V. So here, V is going to be the matrix of entries. First column corresponds to first vector, 1, 1, 1. Second column corresponds to second vector, 1, 2, 0. Third column corresponds to third vector, 0, negative 2, 1. And this right here, this matrix V, is precisely how you change from the V basis to the standard basis. Because you can see that if you look at the coordinate vector in the V basis, say 1, 0, 0, this corresponds to simply the vector V1. And if you multiply this by V, what do you get? Well, you get 1, 1, 1, which is the vector representation of V1 in the standard basis. So V here is how we switch from the V basis to the standard basis. Now, this tells us, according to the work we just did, that A should be the same thing as starting up here, going down from the standard basis to the V basis, and then going over by the matrix B, and then going up by the matrix V. So this tells us that A here is the same thing as B V inverse V, or equivalently, it tells us that B is equal to A V inverse on the left and V on the right. So we know what V is. We have V. We know what A is. The only thing we're missing to figure out B is we're missing V inverse. But once we have V inverse, we can multiply these three matrices, and that will give us B. And we will have the representation of B with respect to the V basis. So the first thing we want to do is we want to take our matrix V and we want to find its inverse. So let's go about that computation. We simply take this, and we're going to regard it as an augmented matrix. So I'm going to get rid of this right here. And I'm going to put the identity matrix on the right. So this is V augment I. And what I'd like to do is I'd like to perform row operations to this augmented matrix so that the left side of the augment becomes the identity, which in turn will make the right side into V inverse. So I'm going to do my operations. First thing I'm going to do is I'm going to set row 2 to be equal to row 2 minus row 1. I'm going to set row 3 to be equal to row 3 minus row 1. And this will clear out this one and this one. So I'm going to have 1, 0, 0, 1, 0. Here I'm going to have 1, negative 2, negative 1, 1. On the other side of the augment, I'll have 1, negative 1, negative 1, 0, 1, 0, 0, 0, 1. Next thing I'm going to do is I am going to clear out this negative 1. So I'm going to set row 3 to be equal to row 3 plus row 2. So I'm doing that type 3 row operation. If I do that, I have 1, 1, 0, augment 1, 0, 0, 0, 1, negative 2, negative 1, 1, 0, and then 0, 0, negative 1, and then negative 2, 1, and 1. All right, so this is looking good. Next thing I'll do here is I will set, how about I do one more, I'll factor it. So I will do an extra operation here, which is I'm going to set row 3 to be equal to negative row 3. So I get 1, 1, 0, 0, 1, negative 2, 0, 0, 1, 1, 0, 0, negative 1, 1, 0, negative 2, and then 1, or I'm sorry, this should now be flipped. So I have a positive 2 here, a negative 1 here, and a negative 1 here. Now I can use this one and this one to begin clearing out these entries. So I'll do it in 2 steps. First thing I'll do is I will set row 2 to be equal to row 2 plus 2 row 3. If I do that, I'm going to have 1, 1, 0, 0, 1, 0. I'm sorry. Yeah, that's correct. And then 0, 0, 1. Over here, I'm going to have 1, 0, 0. On the bottom, I'll have 2, negative 1, negative 1. And now I have to do a little bit of calculations. So if I multiply this by 2 and I add it to this, I should get a 3 here. I should get a negative 1 here and a negative 2 here. Final step is I set row 1 equal to row 1 minus row 2. And now I'm going to have the identity on the left-hand side. And on the right-hand side, I'm going to have, well, the bottom 2 rows won't change. So let me fill those in first. Now let's figure out what happens to the top row of the augmented side. I'm subtracting 3 from 1, so I should have a negative 2 here. And I am subtracting negative 1 from 0, so I should have positive 1 here. Subtracting negative 2 from 0, so I should have a positive 2 here. So this suggests that V inverse is negative 2, 3, 2, 1, negative 1, negative 1, 2, negative 2, negative 1. let me quickly sanity check myself to make sure this worked. So for example, if I multiply this first column by this first row, I get 1, which is exactly what I'd expect. If I multiply this first column by this row, what do I get? Does it seem off to me? It seems slightly off. Hold on. Let me make sure this is what I want. Something went wrong, sort of. So let's go back here. It's with this entry, I think. Did any of you catch my arithmetic error? Okay, sorry about that. was just briefly experiencing technical difficulties. So let's try to resume this. I had a small arithmetic error here. I want to find where it showed up. So let me go through all this real quick. First thing I did was I subtracted row 1 from row 2 and row 3. So this first calculation looks correct. Second thing I did was I took row 3 and I added row 2 to it. Okay, I think I see what may have happened. So if I add row 3 to row 2, I should get this, this, this. Okay, this is still good. Next thing I do is I negate row 3. I get a 1 here, so this is still good. Did I lose anything along the way? It does not look like I did. And so the next thing I do is I add 2 times row 3 to row 2. So let's do that. This cancels. This becomes 3. This stays 1. That looks good too. Final thing I do is I add let me just do something real quick. If I do -2 plus 6 minus, oh, never mind. Looks like I don't have an arithmetic error. I was just being an idiot when I was checking this. I have correctly computed V inverse, which means I can move on to the next step, which is I take my V inverse and I go down here. So I have V inverse, I have V, and I also have my matrix A, which I will transcribe right now. So A here is 3, 2, 2, -1, 0, -1, -2, -2, -1. And the final thing I need to do is I need to compute B, and I can compute B by the similarity relation, which I wrote at the very beginning. So let me grab that and bring it down here. So now I have all the data I need to solve my problem, and it's merely a matter of bringing it all together. So let me organize it. First thing I'm going to do is I'm going to multiply V here with A. So I'll take this, and I'll take this, and then after I've multiplied these two, the next thing I have to do is I have to multiply V inverse. So we have to do this calculation right here. So let's go about it. It'll take a minute. First thing I'll do is I'll multiply this and this, and I'll leave this for after. So I'll have -2, 3, 2, 1, -1, -1, 2, -2, -1, and then the product of these two things. So if I multiply this first column by this first row, I see that I get 0. If I multiply this first column by this second row, I see that I get 0. Likewise, if I multiply this first column by this third row, I get 0. If I multiply the second column by this first row, I see that I get 1. Down here, if I multiply this by this, I see that I get 2. And this by this, I see that I get 0. Now if I take this third column and I multiply it by this first row, I see that I get 0. I take this first column, or third column, multiply it by the second row, I get -2. And then I take this third column and multiply it by this third row, and I get 1. So now I have to multiply this by this. And so this is the final step of the computation. I'm going to get 0, 0, 0 here. That's easy. When I multiply the second column by this first row, I get 0. When I multiply this by this, I get 1. When I multiply this by this, I get 0. When I multiply this by this, I get 0. When I multiply this by this, I get 0. And finally, when I multiply this by this, I get +1. So with respect to the basis V, the matrix B is given by the matrix 0, 0, 0, 0, 1's here, and 0's everywhere else. So we calculated our transition matrix, and we used our transition matrix to compute the matrix B in terms of the matrix A. So this is how similarity problems go. You're given one matrix to begin with, usually, or a linear transformation, which you then have to write down the corresponding matrix. Then you have to figure out the change of basis maps between the corresponding coordinate vector spaces. Then you use the two matrices you have, and one of them you have to use its inverse, in this case V, and you use that to compute B. So this is how similarity problems go. And before I finish, let me explain to you why this is all important. Depending on the basis we choose, we can often put our linear transformation in a much nicer form, where its properties are easily observable. So to run with the example we just computed, let's note that the A we started with was this. And take this, bring it over here. And if you look at this matrix, you just see these numbers and you don't kind of see any special structure to it. And if I was to ask you a question like, for example, does A have a kernel or a null space? You'll have to actually take this matrix and do a sequence of computations to figure out whether it does or it doesn't. On the other hand, if we look at the matrix B, which we computed, we see immediately that the matrix B has a kernel. And in fact, the vector 1, 0, 0 spans the kernel. So this tells us, consequently, that V1 is in the kernel of L. Our linear our original vector V1, this thing right here. So depending on what form we have our matrix in, we can often more readily eyeball and spot properties of it. Right now, in this specific problem, we switched from a matrix that was kind of messy to a matrix where the only non-zero entries occurred along the diagonal. And when that happens, it becomes very, very easy to answer various questions in linear algebra. And a problem we're going to deal with very, very soon is how do we find bases such that with respect to that basis, the matrix associated to the linear transformation takes on a particularly nice form. This is going to be the eigenvector problem, and it's going to be probably the most important thing we talk about in this course. But before we get to it, we have to do a few other things. In particular, we have to look at orthogonality. And this brings us into chapter 5. And this is the next big topic for us. So, orthogonality is something that most of you have probably seen at some point in your life. For example, when you took a multivariable calculus course. But because for many of you it may have been, a little bit since you've seen it, I'm going to do a review, at least of the cases that you've seen before. And then I'm going to talk about how we generalize it to higher dimensions. So I'm going to start with orthogonality. In R2 and R3. So R2 and R3 are both vector spaces, as we well know at this point. But when you're studying them in multivariable calculus, they're not just vector spaces. They come to you with a little bit of extra structure. So in multivariable calc, these spaces have extra structure. Given by the scalar product. Or maybe you've seen it called the dot product. So sometimes people call it the dot product, other times people call it the scalar product. And what it does is, for example, say I have a vector AB in R2 and a vector CD in R2, then the dot product / scalar product of these two vectors is simply A times C plus B times D. Likewise, we could do the same construction in R3. So if we had ABC here, the dot product of ABC with XYZ would simply be AX plus BY plus CZ. So the dot product takes two vectors and returns a number. So to do a very stupid example, what we could do is we could look at, say, the vector 5, 3, and we could take its dot product with the vector 7, 1, and this will be the same thing as 5 times 7 plus 3 times 1, so 35 plus 3, which is 38. Now, as you've probably seen, one important application of this dot product is it allows us to have a notion of distance. So if V is in R2 or V is in R3, we can use the scalar product to form a notion of distance. And the way we do this is we simply we take two bars, we put them around our vector v, and this is sometimes called the length of v, and it is defined to be the square root of v dot v. Now, because this is linear algebra, we have yet another way to think of this. So first off, note that if we look at, say, how about we start with v dot u? So this will be the same thing as v1, v2 dot u1, u2. This will be equal to v1, u1 plus v2, u2. Well, we can think of this slightly differently, which is that we can think of this as the result of a matrix multiplication. And so the matrix multiplication we'd be performing is the row vector v1, v2 with the column vector u1, u2. So we can alternatively write v dot u as v transpose matrix multiplied with u. So this is a way of reformulating the dot product in terms of the matrix multiplication product. So what you can actually do now is that we can generalize this notion. And so here is what we really want. Given vectors v and u in Rn, so we're no longer expecting n to be 2 or 3, we may define the scalar product of v and u to be v transpose matrix multiplied with u. Likewise, we may define the length of v to be equal to the square root of v transpose matrix multiplied with v. So this is how we can conceive of a scalar product in an arbitrary real dimensional vector space. I should emphasize here that this scalar product is defined for Rn, and so in particular it's defined using the standard coordinate structure on Rn. And so for various reasons, this is called the standard scalar product. In some sense, because it corresponds to the standard basis. There are other scalar products with different properties, but for the purposes of what we're going to do today and, well, the next two classes, it suffices to work with the standard scalar product. So before I move on and talk about this general standard scalar product, I just want to do a few more review a few more ideas that come up in multivariable calculus. So first off, why don't we just compute the length of a vector real quick? So say I try to compute the length of the vector 0, 3, 4. So this is a vector in three-dimensional space. Well, this will be the same thing as the square root of the row vector 0, 3, 4 matrix multiplied with the column vector 0, 3, 4, which will be the same thing as the square root of 0 squared plus 3 squared plus 4 squared, which will be the same thing as 0 plus 9 plus 16 square root of 25, which is simply 5. So we have successfully computed the length of this vector. And you've surely done calculations like this in a multivariable course at some point in your life. But now we can do similar calculations in higher dimensions. For example, we could look at the length of the vector, maybe say 1, 3, 5, 2. Now this is now a vector in R4, which maybe it's easy to you, but it's never been particularly easy for me to have a very intuitive grasp of four-dimensional space. But even if I can't easily picture four-dimensional space, I can still compute the notion of distance inside of it, simply according to the formula that we're using. So this turns out to be the same thing as the square root of, well, what we do is we take the row vector, 1, 3, 5, 2, which is the transpose of this. We multiply it by the corresponding column vector, 1, 3, 5, 2. This gives us the square root of 1 squared plus 3 squared plus 5 squared plus 2 squared. And if you simplify, this is going to be the same thing as the square root of 39. And we can't reduce that any further. So by using this standard scalar product, we're able to kind of take our geometric intuition and our geometric constructions that we know about from R2 and R3 and import them to Rn. So with that in mind, why don't we review some of the ideas that you kind of encounter in multivariable calc using this standard scalar product? Well, here is an important one. So let me go over here and grab it. We can define the angle between vectors in R2 or R3 as follows. Or actually, not even define the angle, we can use the existing geometric notion of angle. And our first theorem tells us that the standard scalar product of x and y is equal to the length of x times the length of y times cosine of theta. So this shows that somehow the standard scalar product is capturing information about the geometry of how x and y are located in space. The picture to have in mind is you have your vector x, you have your vector y, you also have your angle theta between them, and somehow this angle theta is related to the length of x and y as well as the dot product or the scalar product of these two vectors. So let's prove this. The main fact we're going to use is the law of cosines. So here's what the law of cosines says. The law of cosines says that if you have a triangle, and say here we have A, B, and C, and we have a theta here, then we have to have that A squared plus B squared minus 2AB times cosine theta is equal to C squared. So if you've not seen this formula before, it kind of generalizes the Pythagorean theorem. The Pythagorean theorem is in fact a special case of this, where you take theta here to be 0. And so we're going to use the law of cosines to prove this relation. So first off, let's take this picture over here and slightly magnify it. So I have my x vector, I have my y vector, and I can also look at their difference vector. So this is going to be the vector that starts at x and ends at y. So this precisely will be x minus y. Actually, I'm sorry. y minus x. Now, according to the law of cosines, we have to have the following relations. The length of x needs to be, well, when you square it and you add it to the length of y, and you subtract 2 times the length of x times the length of y, cosine theta, what you get is you get the length of y minus x squared. Now this right here is the same thing as x transpose times x plus y transpose times y minus 2 length of x, length of y, cosine theta is equal to y minus x transpose times y minus x and if you multiply out the right hand side, what you'll get is you'll get y transpose times y minus x transpose times y and then plus, or I'm sorry, plus, actually, sorry, no, minus y transpose times x, and then plus x transpose times x. And if we take this over here, and we simplify the whole expression, what we find is we find that negative 2 times the length of x times the length of y cosine theta is equal to minus x transpose times y minus y transpose times x. But these two quantities are in fact the same, so this is really just the same as minus 2 x transpose times y. And we can divide both sides of this by negative 2, and we find that x transpose times y is equal to the length of x times the length of y times cosine of theta. And so this completes the proof of this formula. This formula has an immediate consequence, which is very important, called the Cauchy-Schwarz inequality, which you may not have seen before. So let's go through it. What we're doing is we're saying, suppose we have vectors x, y in either R2 or R3, then the absolute value of the dot product, or the scalar product of x and y, is less than or equal to the length of x times the length of y. So why is this true? Well, let's look at what we know. We know that x transpose times y is equal to length of x times the length of y times cosine of theta. So we also know that cosine of theta is less than or equal to 1 for all theta, which means the absolute value of x transpose times y is equal to the length of x times the length of y times the absolute value of cosine of theta but since we know that cosine of theta is always less than 1, what we know is we know that this absolute value is always less than or equal to 1. So this is always less than or equal to the length of x times the length of y. And that completes the proof of the Cauchy-Schwarz inequality. And it is a very, very useful one. And here is another crucial definition. And really, it's kind of the heart of why we're doing this review. If we have two vectors x and y in either R2 or R3, then we say they're orthogonal. If x transpose times y, the scalar product of x and y, is equal to 0. To understand the geometry behind this, well, think about it. If the scalar product of x and y is equal to 0, then that means that this quantity has to be equal to 0, which implies if x and y are not equal to 0 themselves, that cosine of theta is equal to 0, which implies that theta is either pi over 2 or 3 pi over 2. In either case, the picture we get is something like this. We have our vector x, and then we have a vector y, and we have a right angle between them. So whenever the scalar product of two vectors in R2 or R3 vanishes, it implies that the angle between them is, well, in some sense 90 degrees, depending on where you measure it from. Now, we can use this in a very fun way. So, suppose V is a vector in R3. Then the set of vectors W in R3 with V transpose times W being equal to 0 is a subspace, and it is a plane orthogonal to V. So the picture you should have in mind is you have your vector W, or sorry, you have your vector V. It points out like this, and then it's orthogonal to a plane, and this plane is precisely the set of all vectors W, with V transpose times W being equal to 0. So let's verify two things. The first thing we're going to verify is that it's a subspace. To see this, what you have to do is you have to check that if V transpose W1 is equal to V transpose W2 is equal to 0, then V transpose A1 W1 plus A2 W2 is equal to 0. But that follows simply from the fact that this is the same thing as A1 times V transpose W1 plus A2 V transpose W2. And we know that this quantity right here and this quantity right here vanish. So that shows that it's a subspace. Second, it's a plane because it's spanned by two vectors. Well, in this case, W1 and W2. And it's orthogonal because every linear combination of W1 and W2 is orthogonal to the vector V. Now, you may not have used these words before, but certainly you have done the following construction. So let me say, how about this? given this kind of problem that you see in multivariable calculus, given 3 points in R3, find the plane containing them. So the way you would usually do this in multivariable calculus is that you draw the following picture. So you have your R3, and then you have your couple points, and you draw vectors from one of the points to the other 2 points. And then maybe you say you call this V, say you call this W. The next thing you do is you form V cross product with W. And you note that V dotted with V cross W is equal to 0. And W dotted with V cross W is also equal to 0. And so that's how you show that this vector right here is going to be orthogonal to the vector V and the vector W, and hence orthogonal to the plane spanned by these vectors. Now, because this is a linear algebra class, we can do this slightly differently. So let's make my example concrete and choose 3 points. So say we choose the point P1 to be simply 0, 0, 0. We choose the point P2 to be 2, 1, 3. And then we choose the point P3 to be equal to the point, how about 1, negative 1, 0. And so these 3 points determine a plane. And the question is, find a vector orthogonal to it. Well, here's how we can approach this problem from a linear algebra perspective. I'm going to take this point and this point. I'm going to utilize the fact that my point P1 is 0, so I don't have to subtract it. But if I did subtract it, it would give me vectors, and the vectors would simply have the same components. And I'm going to form a matrix. My matrix here is going to be the matrix A, where the first row is 2, 1, 3, and the second row is 1, negative 1, 0. So let's take this and go to another slide. To find a vector A, B, C in R3 orthogonal to the plane, we need only compute the null space of A. Because any vector that's in the null space of this matrix is going to be orthogonal to both of these. Well, it's going to be orthogonal to the vector 2, 1, 3 and the vector 1, negative 1, 0. So, how do we do that? Well, we have some techniques at hand that help us. Simply row reduction. So we write down our matrix. And what we're going to do is we're going to put it in row reduced echelon form. So the first thing I'm going to do here, just to make my life easy, is I'm going to swap row 2 with row 1. So I get 1, -1, 0, and then 2, 1, 3. Next thing I do is I set row 2 to be equal to row 2 minus 2 row 1. If I do that, I'm going to get the matrix 1, -1, 0, 0, and then 3, and then 3. Next, what I do is I set row 3 to be equal to 1/3 of row 3. And I get 1, -1, 0, 0, 1, 1. And the final thing I do is I set row 1 to be equal to row 1 plus row 2. After doing that, I have 1, 0, 1, 0, 1, 1. And so this right here is the row-reduced echelon form of A. So how does that help me in finding a vector orthogonal to the plane? Well, let's see. At this point, I can take it to a new slide. And I note that if I multiply it by, say, a vector, x1, x2, x3, the one here and the one here are going to correspond to the bound variables, x1 and x2, but x3 is a free variable. But x3 free. So this tells us that if I set this equal to the zero vector, 0, 0, I'm going to have x1 plus I should use subscripts. x1 plus x3 is going to be equal to 0, and x2 plus x3 is going to be equal to 0, which is the same thing as x1 being equal to -x3, x2 being equal to -x3. Now I can simply choose x3 to be anything. So how about I take x3 to be 4? If I take x3 to be 4, what that means is that x1 is equal to -4, and x2 is equal to -4. So the vector 4, or -4, -4, 4 is in the null space of A. Why don't we verify that? So what I can do is I can take my original two vectors I had here, call them v1 and v2, and I can compute v1 transpose, times w, where w is -4, -4, 4, and I find that this is equal to -4 times 2 minus 4 plus 3 times 4, which is equal to 0. So this implies that W is orthogonal to V1. And we can also compute V2 transpose multiplied by W. And we find that we get -4 plus -1 times -4 plus 0 times 4, which is simply 0. And this implies that W is orthogonal to V2. So to go over this all again, at some point in your life, you've done problems like this. You've been given 3 points at R3, and you've been asked to find the plane containing them. Usually you do that using the cross product. But now we can reconceptualize it in the framework of linear algebra, and we can do it by essentially what we would do in general, is like if we took P2, P3 here, we would subtract P1. These would give us vectors. We put the vectors in a matrix, and then we find the null space of the matrix. And pick any vector in that null space, and you'll have a vector that's orthogonal to your plane. So this is one way that we're going to start generalizing the ideas of multivariable calculus to higher dimensions. Let's look at one more thing. So you've all probably seen the scalar projection and the vector projection, but I want to look at them again. So here's the way to think of these two quantities, P and alpha. Suppose we have vectors x and y, as in this picture. Well, what we can do is we can try to project x onto y. And by project, I mean orthogonally project. So what we do is we try to walk, imagine you're a person walking along the vector y, and you're looking up directly above you, so like 90 degrees from y. Eventually, you get over here, and if you look up, you can see just the tip of x. And at this point, the line between this person and this point makes a 90-degree angle with y. Then the length of the segment is the scalar projection of x onto y. And it's given according to this formula. So you take x transpose, you multiply it by y, and then you divide by the length of y. So that's one of the notions. Now, suppose we weren't interested in simply the length of this segment, but what we were actually interested in is we were interested in the vector, this red vector, starting from here and going all the way over here. Well, this red vector, this is called P, and P here is called, well, it has a name, it's the vector projection of x onto y, and we can compute it according to this formula. So this is these are two very, very fundamental tools to doing geometry in two-dimensional and three-dimensional space. But they're also tools that we're going to generalize to higher dimensional space, n-dimensional space. So why don't we do a simple example that shows how these ideas can be applied, just as a way of reminder. So consider the plane of the previous example. So it's the plane spanned by this vector and this vector. what we want to do is we want to find the distance of the point one, one, one from the plane. So when I was setting this up, I made it so that this plane contained the origin. So we can picture it something like this. Here's the origin of R3. And we have a point here, 1, 1, 1. And we can draw the vector connecting it. Well, we also have another vector. We have a vector that's orthogonal to the plane. And the vector that's orthogonal to the plane is this one. -4, -4, 4. And what we could do is we could try to figure out the distance from this point to this plane by essentially noting that its nearest point on the plane is over here or something. Maybe right there. And the distance between the point and the plane is given by this blue line segment. And so in order to find this length right here, what we could try to do is we could note that this blue length is the same as this blue length, which is precisely the scalar projection of the vector 1, 1, 1 onto the vector -4, -4, 4. So the distance of 1, 1, 1 from the plane may be understood as the scalar projection of 1, 1, 1 onto -4, -4, 4. So this is just a computation. We take this formula right here and we set our vector x to be the vector -4, -4, 4. We set our vector y to be the vector from 0 to the point 1, 1, 1. So y will just be 1, 1, 1. We note that x transpose times y is simply -4. And the length of the vector x is precisely the square root of 4 squared plus 4 squared plus 4 squared, which is the same thing as 4 times the square root of 3. So this tells us that the distance of 1, 1, 1 from the plane is -4 divided by 4 times the square root of 3. And because we want our distance to be positive, we may as well take the absolute value of this. And this just gives us 1 over the square root of 3. So this is one way that we use scalar projections. Compute the distance from a vector onto a plane. The general problem that we're going to want to deal with, and we're going to start looking at it next time, is things like this. Given a vector v in Rn and a subspace S in Rn, find the distance from S to V. And the way we're going to approach this is exactly the way we just did it in 3 dimensions. Now, the thing is, when we go up to higher dimensions, we don't have such pretty pictures anymore. We can't easily visualize n-dimensional space, but what we're going to learn is that the computations we have to do, like say finding the distance between a vector and a subspace, is exactly the same kind of computations we did in R3, and they'll be formally similar. So, with that said, let me now give you guys the fundamental definition, and this will be truly a new thing. So suppose we have 2 subspaces X and Y of Rn. Then we say that they're orthogonal if X transpose times Y is equal to 0 for every X in X and every Y in Y. And if X and Y are orthogonal, we write this. And so this is read, X is orthogonal to Y. So we already have one example of this, namely the one we just did. What we can do is we can take the span of the vector 4, or negative 4, negative 4, 4, and we can also take the span of the vectors 2, 1, 3, and negative 1, 1, 0. So I'll call this X, and I'll call this Y. Then X and Y are orthogonal spaces of R3. Let's do another one. So suppose I look at the following 2 objects. I'm going to stay in R3, and I'm going to set my X to be the span of E1 and E2, where these are the standard basis vectors. And I'm going to set Y to be the span of E1 and E3. Then I can visualize X and Y as follows. Well, X and Y simply form the XY plane. Or I'm sorry, E1 and E2 simply forms the XY plane, so this is the subspace X. Y1 is spanned by E1 and E3, so it forms the XZ plane. So it looks something like this. And so now you have a space X and a space Y. These are both planes. And if you look at them, you'll note that the angle between them is 90 degrees. And so you are tempted to say X and Y are orthogonal. Unfortunately, this is false. In order to see why this is false, note that E1 is an element of X and E1 is an element of Y. And so E1 transpose times E1 is simply equal to 1. But this can't happen if X and Y are orthogonal subspaces according to this definition. So even though, this kind of looks geometrically like these two planes are orthogonal, they are not orthogonal in terms of our new definition. I'm going to prove one property of orthogonal subspaces today and defer the rest until Friday. Actually, you know what? I am simply going to wait and do it all Friday because it's better logical progression. Anyways, I hope you guys have a nice rest of your week. I will post the homework that will be on similarity and linear transformations as soon as this lecture is over, and it'll be due next Monday. Good luck, and